I'm Jose. I'm Casey.
I'm Fritz.
And in this video, we're going to be defining some sound and audio terms for you.
And also measuring a standing wave.
Warning, this is an auditory piece. Warning, I repeat.
So I've got 3 definitions for you. First definition is wave propagation. Wave propagation is essentially just how the sound of the wave travels through a medium, like air or even this wall. There's compression. Compression is the part of the longitudinal wave where molecules are more densely packed, and the refraction is the opposite of that. It's the part of the wave where the molecules are less densely packed.
Alright, I got 3 more definitions for you. The first is wavelength. And this is pretty self-explanatory. Essentially, it is the length of the wave. Next, amplitude. Amplitude is the height of the sound wave, which is often perceived as volume, but careful because this is not the same thing. Then we have frequency. Frequency is the amount of cycles in a sound wave, and this is perceived as pitch.
Okay, so we have many other more terms. For example, we have timbre, which is like the color of a sound. It's basically determined by the overtones in the sound, and overtones the same as harmonics actually, which are naturally occurring higher frequencies above the bass tone. And with waves, you also have waves in phase and waves out of phase. So a wave that is in phase is when 2 sound waves of the same frequency are basically aligned together, and when they are not aligned, they're out of phase.
I have one more definition for you. Standing waves. Standing waves happen when sound waves bounce back and forth in a straight line, and then it creates a combination of multiple waves moving in opposite directions, and it sounds very bad.
In order to calculate the standing wave, we need to use an extra special formula. And this formula is velocity equals, come in, closer, wavelength times frequency. So, with my trusty iPad, I measured the length of the room, and it came out to 11 feet, almost exactly. If we plug in our knowns, we get 11 feet for the wavelength, 1,130 feet per second for the velocity, and we need to find the frequency. So what do? We divide both sides by 11, and that gives us 102.72 hertz.
I got a feeling that tonight's gonna be
These 2 walls for the frequency and the standing wave. These 2 walls. We're gonna use the same formula, but we're gonna use 7 instead of the original wavelength because it's the new wavelength. So 1130 divided by 7 equals 161.42 hertz, which is the frequency of the new standing wave.
So I have some more math for you. We have 4 frequencies for each measurement. Now for the fundamental of the first measurement, we take the velocity divided by half of the wavelength, which equals 205.45 hertz, and that's our base frequency or fundamental. The second frequency, we already calculated. It's just the velocity divided by the measurement of the room, which is 11 feet. For the third frequency, we take the velocity divided by the wavelength times 3 halves, which equals 68.48 hertz. That's our third frequency. And for our fourth, we take the velocity divided by twice the wavelength, which is 22, which equals 51.36 hertz. For the second and third measurements, which are the same, we take the velocity divided by half of 7, or 3.5, which equals 322.85 hertz, which is the fundamental. Then divide by 7, 161.42 hertz. The velocity divided by 7 times 3 halves, which is 107.61 hertz. And the velocity divided by twice of 7, which is 14, which equals 80.71 hertz.
Okay, so because the ceiling and the floor here have the same distance as this wall to this wall, that means that the standing wave frequency is the same from both distances.